What we're going to do is we actually only have two more examples to go in the topics we've been talking about, which is obviously relatable to obviously our experiments and stuff that we're doing. So we're going to take the first little bit here. We're just going to kind of finish up the last couple of examples here in terms of molecular formulas, empirical formulas, again, to make sure, again, everybody's on the same page and stuff like that. So like I said, I think we only have like two more, this one and one more to go. And then we'll actually be kind of officially done with this topic, which obviously relates to the experiments and stuff we're doing. So we left off here with this particular one. So why don't you take a few minutes and work it out. We're actually looking for both the empirical formula and the molecular formula on this one and see what you come up with. We got some percent compositions given to us of phosphorus and oxygen, and I'll give you some numbers in case you don't have it. Phosphorus is 3097 from the periodic table. Oxygen is 16. All right, so we're looking for two answers here, just like we've been doing in the last several examples earlier today. We're looking for the empirical formula and the molecular formula in this situation here. So take a few and see what you come up with, and then we'll go over it, and hopefully everybody ends up with the same answer. Okay, so let's take a look and kind of see how we're doing. So in this case, we're actually looking for both things. We're looking for the empirical formula and the molecular formula, which is kind of a good thing because really for the molecular formula, if you remember, you need basically the empirical formula, so that's good. You do obviously need the molar mass of the compound, which was given to us right here at 283.89. And lastly, for the molecular formula, you need basically the molar mass of the empirical formula. So really, since we need to calculate the empirical formula anyways as part of the problem, and we needed really just to do the molecular formula part, we could really just start with the empirical formula type of the problem, just like we normally would. Again, we are given the percentages by mass of each of the elements that are present. That is a situation where we can safely assume 100 grams that we're starting with. And as we talked about, what that essentially does is just basically turn our percentages into grams. So that basically means that we would have 43.64 grams of phosphorus. And that would also mean that we have 56.36 grams of oxygen. And again, by making the sort of that assumption, it keeps the numbers the same and does a very quick conversion, obviously, from percentages into grams, which is a more usable sort of number for us to use in this calculation, because our next step is to basically get our numbers into moles, and we could easily do that from grams by using the molar mass here. So we would use our molar masses to convert these grams into moles. So taking our phosphorus, putting the grams on the bottom, which is 3097. And for our oxygen, also 16 grams on the bottom there. We'll turn our percentages from grams into grams and our grams now into moles. And it looks like we are going to hit something like 1.409 for our phosphorus. And for our oxygen, looks like we will hit 3.5 to, we'll round it to 3 here, moles of oxygen. Any questions so far on that? At this point, now that we've gone from grams to moles, we want to find the one that's the smallest number of moles, and we want to divide by it. In this case, it looks like it is the phosphorus. So we're going to divide everybody by the moles of the phosphorus, which is the smallest, always the smallest when we're doing this. And that gives us obviously 1 for the phosphorus. And when we do our oxygen, that gives us a 2.5. That means if we took our empirical formula at this point, it would be PO 2.5. The problem with that is, as we talked about, you do need whole numbers here. This is not a whole number. This is, again, in a textbook type problem and those type of problems like exams, quizzes, this is too far to round. So you cannot round at this point. You can't round up or anything like that. So this is the part where we do need to figure out a basically factor to multiply this empirical formula by to get all whole numbers. And again, trial by error is just a simple way of doing that. 2.5 times 1 obviously is 2.5. 2.5 times 2 gives us 5. And that is a whole number, but the importance of it is this is the factor by which we need to multiply our empirical formula by to yield the simplest whole number ratio. So we're going to multiply our empirical formula here by 2. And when we do, we end up with P205. And that is whole numbers all the way across. And that would then be our correct empirical formula. Again, we cannot use this because of the 2.5. Any questions up to that point there? So that pretty much is all the same steps that we did earlier to calculate our empirical formula. And again, in a textbook problem, as I mentioned a number of times, really shouldn't be doing any rounding unless it's like pretty much right on that whole number, just like right before the whole number, like 0.99-ish, 0.98, 0.97, or just above kind of the whole number, 0.02, 0.03, something like that. But again, common ones you come across, 2.5, 0.33 type of numbers. These are numbers where it's too far to round. So for the empirical formula, you do need to find that factor to multiply it by. Any questions on that? Okay, so the next thing we want is our molecular formula. So we've now just got the empirical formula. We know the molar mass of the compound from the problem. So now we can get the molar mass of our empirical formula. And that would then be 2 times 3097 for our phosphorus, plus 5 times 16 there for our oxygen. That's going to give us an empirical formula molar mass of 2 times 30.97 plus 5 times 16. Looks like about a 141.9. So what we're going to use that molar mass and the molar mass that was given to us in the problem, and we're going to basically divide it. So we're always going to take kind of a larger molar mass-ish in most cases, or the molar mass of the compound that's provided to you, divided by the molar mass of your empirical formula that you calculated. And again, in this case, it should give us a whole number. If it doesn't give us a whole number, this is really the only place in a textbook problem where it's probably okay to round. In this case, we get basically 2. And that 2 is, again, the factor by which we multiplied the empirical formula by to get us to our molecular formula. So we're now going to take our empirical formula and multiply it by 2, which if we go through everybody there, P4O10 looks like a winner. And that would be our molecular formula. Again, older books, and sometimes people would kind of write it like this. I personally think perhaps you should distribute the 2 in there, but you may sometimes see it like this. But most people will distribute it, the 2, and write it like that. Any questions on any of those steps along the way? So you can see in a sort of figure out a molecular formula problem, one approach is basically just to kind of do what we did previously, get our empirical formula first, and then using the information from the empirical formula, then go to our molecular formula. I'm going to now show you this problem worked kind of backwards, if you will, where we will actually start with the molecular formula and then figure out the empirical formula for it. So just to give you another option as to how you can sometimes do these type of problems. You could really do these type of problems sort of backwards, if you will. And what I mean by backwards is sort of starting with the molecular formula and then working yourself to the empirical formula. And you could do it in problems where you really are given the percent composition by mass. So that is sort of the correct way. No, you definitely shouldn't. So the question is about, I think, rounding to 2.5. No, you shouldn't round the 2.5 at all. In this case up here, if this is the 2.5 we're talking about here, it really shouldn't be rounded ever. Again, unless you got something like I said, like, maybe like it was like 2.01 or something like that, then you could round the 2. It's okay. But definitely when you start getting like 2.25 or something like that, or 0.33 at the end, or 0.50 or so forth, these guys are very common sort of decimal parts that you get when you divide it out, and those guys are really too far from the whole number to round. It really does has to be pretty darn close, or like 1.998 or something like that, or 1.98 you could round it to, so something like where the decimal part of it really didn't hit the whole number, either went below it or above it, probably because you did a little bit of rounding with your numbers. But if you start hitting some decimals parts that look like 0.33 or 0.5 or like 0.25 or something like that, those are a result of not really just your rounding, but it's really because the numbers are kind of far from the whole number. So you do need to find the factors. Again, you can sometimes get situations like this or like that, where it's like 0.98 or 0.97, and it's just really more your rounding rather than the kind of numbers and stuff like that. So definitely, and I would say probably 9 times out of 10, if you got a decimal that, like that 0.5, 0.33, 0.25, definitely should not be rounding for an empirical formula sort of calculation. Other questions on that? Okay. And again, like I was saying before, the only place really in sort of a textbook problem where you could round and it's probably okay is at this point where you're trying to do this calculation right here for the molecular formula. And the reason it's okay to sort of round here is the relationship between the molecular formula and the empirical formula is really a whole number relationship. Like one is like a whole number relationship to each other. And that's why in this case, like we got a previous one, it was like 2.16. We rounded to 2. It was okay here. And that's really because in a lot of cases and problems where they give you this sort of number, like where it says the molar mass of this compound is 283.89, it's sort of an approximate molar mass, which means it might not be the correct molar mass. And that's why you could sometimes round there. Even you may have a problem, and we may have one coming up next, where you're even given the molar mass in like a range. Like they'll sometimes say, hey, the molar mass of this compound ranges from like 90 to 110. And they don't give you an actual number of it. And that's why, sort of what I was saying earlier, this is sort of the only place in a textbook problem where it's probably okay to round if you don't hit a whole number, but definitely not in this case up here in the empirical formula part. You really shouldn't round unless it's super close to the whole number. Other questions on that? Okay. So as I was mentioning here just a second ago, this is a common sort of approach, going sort of the empirical formula to the molecular formula approach. But in situations where you are given the percent composition by mass of the elements, and you're given, the approximate molar mass of the compound, you actually can work it sort of backwards in a sense, go from the molecular formula back to the empirical formula. So let me just show you how that problem would look on this guy here. Let me find it. We just rewrite those numbers there. So basically what they told us was that this compound was 43.64% by mass made up of phosphorus. and 56.36% made up of oxygen. And approximately the molar mass of this guy is about 283.89 grams per mole. So what these numbers represent, as we've been talking about, is the percent composition by mass, which means out of that 283.89 grams of this compound, which is basically phosphorus and oxygen made up of that, 43% of it is made up of phosphorus and about 56% of it is made up of oxygen. So if we kind of go the molecular formula approach first, because we have this percent composition of each of these, what we could do is turn these guys from a percentage into a decimal, right? And we do that by dividing by 100 or moving the decimal point 2 places to the left. And if we do that, that means we would have 0.4364, which is basically 43.64% phosphorus. And if we times that by the molar mass of the compound, we see that out of that 283.89 grams, basically 43.64 times 283.89, basically about 123.89 grams of it is phosphorus. Right? And if we do the same thing for our oxygen, converting that into a decimal, 0.5636% times the 283.89 grams per mole tells us that out of that 283.89 grams, approximately 160 grams of it is oxygen. So what we just figured out is basically the percent composition by mass of the compound basically contains about 123 grams of phosphorus and about 160 grams of oxygen. We now can convert these into moles using the molar mass of each of these elements, right? And if we do that, the phosphorus was 3097 grams per mole, and the oxygen was 16 grams per mole. And what this is going to give us when we divide that, so 123.89 divided by 3097 yields us a 4 moles of phosphorus. And if we take 160 divided by 16, yields us 10 moles of oxygen. This is going to be our molecular formula that we found, which would be P4, oops, I'll write it right, O10, there we go. P4O10 would be our molecular formula. So because we know the percent composition by mass of each of the elements, and we know the molar mass of the compound, which is basically the molar mass of the actual compound coming from the molecular formula, we actually can get the molecular formula first in this case. And as you can see, it obviously matches the molecular formula that we got over here. Now, once we have the molecular formula, we know that the definition of the empirical formula is the simplest whole number ratio. And from the molecular formula, we see that there is basically 4 moles of phosphorus for every 10 moles of oxygen. That's a 4 to 10 ratio, which if you divide by 2 is a 2 to 5 ratio, which would be the simplest ratio, which means we could reduce this down to P2O5. Again, 2 for the phosphorus, 5 for the oxygen, and we could get to our empirical formula. So this is another approach that you could take, and it's easily done when you know the percent composition of each of the elements and you actually know the molar mass of the compound. You actually can take the percentage, which is basically what we did here. Basically took the percentage times the molar mass, gives us the grams of the one element, do the same thing for the other guy, gives us the grams of the other, divide by the molar mass, gives us the moles that you would have in the molecular formula, reduce down the molecular formula to the empirical formula. And you can see, obviously, just like we got on the previous page, ends up same deal. So again, that's an alternative approach. Sometimes people like to work that way. And again, as long as you know the sort of the percent composition, either you calculate it or it's given to you, you could sometimes work the problem backwards in that sense. Any questions on how to kind of go in that direction? The key is you want to make sure you understand which one you're calculating. So obviously, if you take this approach, you're going molecular formula first to empirical formula. If you take the more traditional approach like we've been doing, you're going from empirical formula to molecular formula. So, it's important to keep those things separated and understand how to do them. Any questions on either approach there in terms of doing that? Okay. Let us then take a look at one last one here to kind of finish up our conversation here about empirical and molecular formulas. So go for it on this one here. We got some vitamin C. It has a molar mass of 176.13. What is the empirical and molecular formula here for this one? Look here. So we want to find empirical and molecular formula. So I just showed you a couple different approaches. So we'll take a look at both of them real quick here just to make sure. So we'll start with the more sort of traditional approach. Again, going empirical formula first, followed by molecular formula. So in this case, we do have the percent compositions given us for each of these elements. We will again, if we're going empirical formula approach first, we're going to assume 100 grams. Again, that just gets us getting rid of really these percentages and turning them into grams. So if we assume we had 100 grams, that means we should have 40.9 grams of carbon. We then would also have 54.5 grams of oxygen. And I think I missed the guy in the middle there, 4.58 grams of hydrogen. I think got everybody in the right spot there. We then would, in our normal empirical formula sort of approach, go to the periodic table, use the molar masses, and convert each of these into moles. So that's going to be 12.01 grams per mole for carbon. That's going to give us 16 grams per mole for our oxygen, and our 1.008 grams per mole for hydrogen. And if we do all that good stuff there, 40.9 divided by 12.01, looks like we'll call it, I put my pen there, 3.41 moles of carbon, 54.5 divided by 16, 3.41 basically moles of oxygen, and 4.5 divided by 1.008, 4.54 moles of hydrogen. Like we've done before, at this point, we're looking for the smallest number of moles. We're going to divide everybody by that. And in this case, it does look like it is the 3.41 is our smallest. That obviously gives us a 1 here, a 1 there, and 3.41, a 1.33 here, which if we kept these numbers here for our empirical formula, that means we're looking at something like C, I'll put the H next, H 1.33 and the O here. This again is not a correct empirical formula because of this number. And again, as I talked about before, you cannot round here. So you should not round here. And that means we do need to find a factor by which to multiply the entire empirical formula by to get us to a whole number. And again, if you did 1.33 times 1, 1.33, 1.33 times 2, 2.66, 1.33 times 3 is 3.99, and that is close enough to 4, right? 9.99, pretty close. So we can basically use that factor of 3 to multiply the empirical formula by. And if we do that, that will then give us, for our empirical formula, C3H4O3 as our empirical formula. Any questions on that up to that point there? Okay, so now that we have our empirical formula, which is sort of the first step that we need to get to our molecular formula, we have the empirical formula, we have the molar mass of the compound given to us. So the other thing that we need is really the molar mass of our empirical formula. And in this case, we got 3 times 12.01 plus 4 times 1.008. And lastly, 3 times 16 for the oxygens. And if we add all that together, 3 times 12.01 plus 4 times 1.008 and plus 3 times 16 there. Looks like we get something like 8806 as our molar mass. At this point, to find our sort of factor to get us to our molecular formula, we take the molar mass that was given to us in the problem of what the compound should be, divided by the molar mass of the empirical formula, which is basically the simplest whole number ratio of what is there. And we're not going to multiply by 100. We're just going to divide it. So 176.13 divided by the answer gives us an approximate 2 as the factor by which we need to multiply our molecular formula by. That means if we do that, multiplying everybody in the empirical formula, it gives us C6, H8, and O6. And again, this would be our molecular formula. And again, sometimes people years ago would kind of do this move. But most people, again, will sort of distribute it out. Question on any of those steps going from empirical formula to molecular formula. Now, if you chose sort of the approach that we talked about a second ago before we did this one, you could definitely do that. Here we are given the percent compositions of each of the elements, and we are given the molar mass of the compound, which really does come from the molecular formula. So here you could go from the molecular formula backwards and take that approach. So just to again show you how that would look if you chose to do it that approach. Here we had 40.9% carbon, 4.58% hydrogen, and 54.5% oxygen with a molar mass of 176.13. So here we would basically convert these percentages into decimals and multiply it by the molar mass of the compound. So for carbon, we would have 0.409, which is 40.9% converted into a decimal. We would multiply it by the molar mass of the compound. And that would tell us that out of the 176 grams or so that we got going on there, about 72.04 grams of it is carbon. We also could do the same thing for hydrogen. Again, moving the decimal point 2 places to the left, or dividing by 100 gives us 0.0458% times 176.13 tells us that, again, out of that 176.13, about 8.067 grams is hydrogen. And lastly, for our oxygen, 54.5% converted into a decimal, times our molar mass here. Gets us about 95.991 grams of oxygen. At this point, again, each of these masses are based off of the molecular formula's molar mass, which is basically what this is. It's basically the molecular formula's molar mass. So now that we know how many grams there are in each of those, we could just convert them into moles by using the molar mass from the periodic table for each of these elements. And we'll see how we did here. Hopefully okay. 16.00 grams per mole. That tells us that the molecular formula should technically contain roughly 5.998 moles of carbon. This, again, as you can see, we've been talking about where to round and where not to round. This definitely can be rounded to 6, and especially since it's the molecular formula, we can round it here to 6. We talk about 8.067 divided by 1.008. This gets us essentially 8.00297, basically moles of hydrogen. Obviously, it can be rounded here to 8 for our molecular formula, moles of hydrogen, and 95.991 divided by 16. Again, we hit something like 5.999 and change moles of oxygen. Again, super close to the whole number. No problem rounding in this situation here. This then gives us, as we talked about earlier, our molecular formula if we go this approach, which hopefully should be the same molecular formula that we got on the previous slide, and it looks like it is, right? At this point, if you take this approach, now we're just going to kind of use the definition of empirical formula, which is the simplest ratio what's present. And from the molecular formula, we see basically 2 moles of six moles of carbon for every 8 moles of hydrogen for every 6 moles of oxygen in this case. Looking like if we go by 2, we can reduce everybody down by. We divide the 6 by 2, that reduces it down to 3 carbons for every 4 hydrogens for every 3 oxygen. Can't go any further down without getting decimals or anything like that. And so this is as far down as you could go in terms of whole numbers, which means our empirical formula then would be C3H4O3 like we got on the previous page there. Our empirical formula. Any questions on either approach, I guess, or molecular formulas, empirical formulas in general? Okay, so just to finish up this and also tie this in again, obviously this is what you're doing in your experiment and all this kind of stuff. So just so we're clear, when we talk about, again, textbook problems, exam problems, quiz problems, homework problems, anything that comes out of a textbook. Again, when you are calculating your empirical formula, and you divide by the smallest, and you really do not hit a whole number. So you hit, like we've seen, 0.33, maybe you hit 0.5 or something like that. These are, again, too far to round. So you definitely should, or maybe like a 0.25, you definitely need to figure out a factor to multiply by. So like we're doing, 0.33 times 1, 0.33 times 2, and so forth. Now, when you are figuring out your molecular formula in these type of textbook problems, and that's when you're basically taking the molar mass of the compound that was given to you in the problem, divided by the molar mass of the empirical formula. If you happen not to hit a whole number, it is okay here to round. I would say in most cases, you will hit a whole number when you do that part of the calculation, but there will be cases where you won't. So for example, just, just to kind of, again, illustrate another sort of example that we're just kind of look at it really quickly here together, this one, and kind of how a problem is worded in situations where you might not hit like a sort of a whole number. So for example, let's just say if we had, let's just say we had a problem where they said, hey, you had 1.52 grams of nitrogen and 3.47 grams of oxygen made up this compound. We want to determine the empirical molecular formula. We'll do the molecular formula here, right? We want to know what is the molecular formula of this guy. And they tell you that the molar mass is between, I get right between there, is between 90 and 95 grams. So here we actually have a range for the molar mass, right? And that sometimes happens in these type of problems because, sometimes empirical formulas are really found experimentally, and molecular formulas, those type of things are sort of found experimentally. So, they have sort of a relative range in terms of that. So if we were to do our sort of normal situation here, we take 1.52 grams of nitrogen, we would divide by 14.01 grams per mole for nitrogen, which again is from the periodic table. That would give us 1.52 divided by 14.01 and 0.1085 moles of nitrogen. We would do the same thing here, 3.47 grams of oxygen. Again, converting our grams into moles. 3.47 divided by 16 gets us 0.2169 moles of oxygen. Dividing by our smallest, as always, gives us 1 and gives us again here 1.9988 here for this. That again, in terms of rounding and where to round, that is perfectly close enough to 2 to call it a 2 at that case. Okay, so this is what I'm talking about, where if you're doing this part, if you're super close to that whole number, it's okay to round. And obviously this is pretty much 2, right? And that's the situation where we're just not at 2 because a little bit of rounding we did here, not because we're really far away from the whole number. So that would be okay situation here to round. That would give us our empirical formula of NO2 as our empirical formula. Now to calculate the molecular formula in this case, we do need the molar mass of it. So the molar mass of this guy then would be 1401 for the 1 nitrogen plus 2 times the 16 for our oxygen. So that's like 32 plus 14.01. That gives us 46.01 grams per mole is our molar mass of our empirical formula. So now when we come to the molecular formula part, right, we're going to take the molar mass that they gave us. But in this particular problem, they really didn't settle on a number. They're like, hey, it could be, kind of between these 2 numbers. So what can you do in this situation? Well, you could do a couple of things if you want. You could actually use the top end of the range. You could use the bottom end of the range. You could even like average and go in the middle there of the range. So if we did the top end of the range, where it was 95 grams divided by 46.01, and we did that, we end up with a number of 2.06, right? Not exactly 2, a little bit over, but again, because this is the molecular formula part and we're dividing these numbers, we're probably okay to call it 2. But what would happen if we took the bottom end of the range here, where it was 90? if we took 90 divided by 46.01, we end up with a 1.956, essentially 1.96. Also, because we're doing the molecular formula here, close enough to round to 2. What happens if we went dead center of that range, right? So if we added them together, divided by 2, right in the middle is like 92.5, right? So if we took our 92.5 grams and divided it by 46.01, 92.5 divided by 46.01, we end up with 2.01. Also, again, close enough to call it a 2. So again, when you're doing the molecular formula part, because a lot of times when you're given a molar mass in the actual problem, it's sometimes even mentioned in the problem in a lot of cases, is sometimes referred to as the approximate molar mass or the apparent molar mass or even the estimated molar mass. You may not hit perfectly every single time a whole number. And again, we're specifically talking about this part of the calculation when we're doing the molar mass divided by the empirical formula's molar mass. And again, that would be the only situation really sort of in a textbook type problem where, you know, if you're a little bit off of the whole number, it's okay to round. But you definitely should not round, you know, in this situation before that, unless it's really, really close, like it was here, or it's like just over it. You know, if you had any of these numbers in this spot, it would be okay to round because it's like 2.01 is just over it. So that's pretty close to 2. But again, the common sort of decimals when you're doing sort of this empirical formula part that you definitely don't want to round, you know, that 0.25, 0.5, 0.33 are very common sort of, you know, decimals that you end up with that you really shouldn't round to the whole number. Any questions on that sort of rounding aspect of it and stuff? Now, when I was mentioning in the experiment that we were talking about last week that it's okay to round, let me also clarify what I was speaking to on that as well. So in the actual experiment, which was experiment 7, you have pre-lab questions, right? So pre-lab questions, you should not be rounding, right? The empirical formula. So just like we did in all these sort of examples today in class, you know, if you end up with, after you divide by the smallest, like a, you know, a 0.33 number, a 0.25 number, you need to find a factor. So pre-lab questions, you could think of them as like, you know, kind of textbook type problems. You typically don't do rounding, again, unless it's very, very, very close. You know, like you got to, like we just talked about, like a 1.02 or something like that. That's okay. But if you got like a 1.33, like we just did, not okay to round in that situation. So you cannot round to 1. You got to find that factor. Post-lab questions, same deal. So if you have post-lab questions that you are finding the empirical formula and you're dividing by the smallest and you don't hit a whole number, you need to figure out the factor to multiply it by, again, as long as it's not just like right at that whole number. The only place in the lab where, again, I was speaking about it's okay to round is in the actual experiment itself. So in the actual experiment and like the data table, from the data information from the video of the actual experiment, like if you were in person kind of doing the experiment, it is there where if you divide by the smallest and you don't hit a whole number, it's okay to round in that part for the empirical formula. So the actual experimental procedure, not procedure, but actually the actual experiment, like if you were hands-on doing the experiment, if you divide by the smallest, you know, when you figure out based on your evaporating dish, you know, how many moles of silver is there, how many moles of chlorides there, and you divide and you don't hit a whole number, you know, you can round in that situation only. So typically only if you're sort of physically doing an experiment and you're using numbers that technically came from an experiment you were performing, in most cases, it's okay to round. Outside of that, in experiment 7, anything that's a pre-lab question, anything that's a post-lab question, you should treat it as, you know, like a textbook type problem that you really shouldn't round unless it's like really on the number, almost like the 0.99 or 0.01 or 0.03. Any questions on where to round and where not to round? So I guess the simplest way to just think about it is try not to round anywhere unless it's very, very close, you know, is usually the good rule of thumb, especially with empirical formulas. Any questions on empirical formulas, calculating, any of those things?